White holes are curious mathematical opposites of black holes.
Not too long ago, people believed that white holes were nothing more than imaginative concepts taken from science fiction. These unusual phenomena were considered purely speculative, found only in the realm of fantasy. However, recent discoveries by scientists have started to change that viewpoint. They've unearthed evidence that strongly suggests white holes might actually exist in our universe. This breakthrough opens up an entirely new realm of possibilities, sparking an overwhelming excitement within the astronomical and cosmological communities. Researchers worldwide are now eager to explore and understand these enigmatic objects. But what exactly are white holes, and what impact could they have on our understanding of the vast cosmos? Come along as we explore how scientists have made history by identifying the very first white hole ever discovered. White holes are theoretical cosmic entities that behave in a fundamentally different way from black holes. While black holes pull matter and light into an incredibly dense core called a singularity, white holes function oppositely. They expel matter and light, preventing anything from entering beyond a boundary known as the event horizon. Picture having a twin who is your polar opposite in every way, disliking the things you like and vice versa. This is similar to the relationship between black holes and white holes. But before we dive deeper into the perplexing concept of white holes, let's take a closer look at black holes. Black holes are some of the most bizarre and captivating objects in space. They are so dense that their gravitational pull is immense, strong enough to trap light itself. In fact, it's believed that the Milky Way might harbor more than 100 million of these ravenous cosmic entities. However, detecting them is not an easy task. Deep within our galaxy, a massive object called Sagittarius A* lurks. This astronomical giant is 4 million times more massive than our Sun and resides about 26,000 light-years away at the center of our galaxy. In 2019, a team of brilliant scientists from the Event Horizon Telescope collaboration achieved something extraordinary. They captured the first-ever image of a black hole, marking a historic moment in science. This black hole resides in the M87 galaxy, situated 55 million light-years from Earth. The scientific community celebrated this monumental achievement, which provided irrefutable evidence for Albert Einstein's groundbreaking predictions from his general theory of relativity, proposed back in 1916. People once didn't even have a name for black holes, with the term only coming into existence in 1967, when American physicist John Wheeler coined it. Prior to this, black holes were simply theoretical ideas in the scientific community. The first confirmed black hole discovered was Cygnus X1, found within the Milky Way galaxy in the Cygnus constellation. Here's how the story unfolded. In 1964, scientists were observing the sky using a special rocket that could detect X-rays coming from space. They unexpectedly stumbled upon mysterious X-ray emissions from an unknown source. The puzzle was solved in 1971 when astronomers realized the X-rays were emanating from a bright star orbiting an unseen dark object. This dark object turned out to be a black hole, and the X-rays were likely caused by the matter from the star being pulled into the black hole, similar to how a vacuum cleaner picks up debris. There are billions of stars scattered across the universe, and roughly 1 in every 1,000 of them has the potential to transform into a black hole. These cosmic giants have such immense gravitational forces that they can even trap light, making them impossible to observe directly. Let's now focus on our home galaxy, the Milky Way, which contains over 100 billion stars. Among these stars, scientists estimate that around 100 million could be black holes, quietly existing within the vastness of space. Finding them is a monumental task, like searching for a needle in a galactic haystack. NASA suggests that anywhere from 10 million to a billion stellar black holes could be present in the Milky Way, each representing a cosmic enigma waiting to be explored. The closest black hole to Earth, known as the Unicorn, resides approximately 1,500 light-years away. It earned its name because it is an exceptionally rare discovery with a relatively low mass, about 3 times that of our Sun. In 2021, astronomers unveiled a striking new image of a gigantic black hole at the heart of the M87 galaxy. Using polarized light, which has a distinct orientation and brightness from regular light, scientists were able to uncover intricate details about the black hole's structure. Polarized light is unique because it reveals information about magnetic fields in a way regular light cannot. By studying how light waves vibrate in particular directions, they were able to analyze the magnetic fields and the behavior of matter swirling around the black hole. The image taken using this method unveiled mesmerizing light patterns that provided deeper insight into the black hole's characteristics. Polarization is a special property of light waves that reveals information about magnetic fields. It's akin to how a compass needle points to the North Pole, showing us the direction of magnetic forces. By applying this technique, scientists obtained a new image of a black hole and discovered that it possessed a magnetic ring surrounding it. Black holes are remarkably mysterious and can be conceptualized in 3 distinct layers. Imagine a powerful vacuum cleaner with 3 parts. The outermost layer is the event horizon, the boundary beyond which nothing, not even light, can escape. Inside the event horizon, there is another layer known as the inner event horizon, a region that is even harder to escape from. At the very center lies the singularity, the heart of the black hole where all of its mass is concentrated in an incredibly small space. This singularity is an immensely dense point in space-time where gravity is so powerful that nothing can break free. Unlike stars and other objects we can see directly, black holes cannot be observed in the conventional way. Scientists instead detect the radiation emitted by matter as it falls into these dark entities. This is similar to how we can observe the effects of something without directly seeing it. Detecting supermassive black holes, which reside at the centers of galaxies, is especially difficult since they often hide behind thick clouds of gas and dust. But here's the interesting part. Sometimes, as matter falls toward a black hole, it can bounce off the event horizon and shoot back outward, creating powerful jets of material that move at remarkable speeds. These jets can be observed from great distances, even if the black hole itself remains hidden. Capturing the first image of the black hole in M87 required an unprecedented effort from a global network of telescopes. The data collected was so vast that it couldn't be transferred over the internet and took 2 years to process. Now, let's shift our focus to an intriguing concept: white holes. While black holes pull everything in, white holes theoretically expel matter and energy in the opposite direction. For a long time, white holes were considered purely theoretical, but some scientists now suggest they could be related to black holes. If you were observing a white hole from a distance, it would look quite similar to a black hole. It would have mass, rotate, and feature a disk of gas and dust surrounding its edge, known as the event horizon. However, unlike black holes, where nothing can escape, white holes would expel objects outward. Imagine a universe-shaking event as the white hole releases previously trapped matter and energy. A white hole operates in reverse to a black hole, as if rewinding a video of a falling object and watching it bounce back up. Like black holes, white holes also have an event horizon, which acts as a limit beyond which nothing can enter. It's like an exclusive club in the vastness of space-time, a region no spacecraft can penetrate. Inside a white hole, objects can emerge and interact with the surrounding universe, allowing matter to escape and venture into space. However, unlike black holes, nothing from the past can enter a white hole, making it seem as though it exists in a separate timeline, disconnected from events that have already occurred. In 1915, Albert Einstein's revolutionary discovery of the field equations forever altered our understanding of gravity and space-time. His equations revealed a startling truth. Space and time are not fixed and immutable, but instead can bend, twist, and fold in response to massive objects like stars and planets. This groundbreaking revelation sparked a scientific race to comprehend how space responds to the matter within it. One of the first physicists to make strides in this field was Carl Schwarzschild, who, within just 1 year, found an exact solution to Einstein's equations. His work led to the discovery of singularities, points of infinite density where space-time becomes so warped that it forms an unreachable region, setting the stage for what would later be understood as black holes. In 1960, mathematician Martin David Kuzel built upon Schwarzschild's work, introducing the concept of singularity. Though he didn't fully understand its implications at the time, his ideas would later prove pivotal as black holes became a recognized phenomenon. Black holes are fascinating entities described by general relativity, but this theory also suggests the existence of white holes, theoretical objects that could expel matter and energy. For a time, white holes seemed to share their fate with wormholes, another theoretical concept, both being considered mathematically possible but unlikely in reality. However, in recent years, physicists have revived the idea of white holes, potentially offering a fresh perspective on black holes and their enigmatic nature. Since the 1970s, when physicist Stephen Hawking proposed that black holes could slowly lose energy and eventually disappear, the question of what happens to the information trapped inside black holes has fascinated researchers. According to the laws of physics, information can't be lost entirely, leading to a mystery about the fate of information inside black holes. While the precise end of a black hole remains unresolved, some researchers suggest that the black hole could eventually shrink down, transforming into a microscopically sized white hole. This new entity would lack the intense gravitational force of its black hole counterpart, but it would contain all the information the black hole once absorbed. In 2006, the NASA Swift satellite detected an incredibly intense gamma-ray burst, GRB, a form of energy released during the collapse of stars. However, this particular GRB, named GRB 060614, did not fit into typical categories and lasted an astonishing 1,002 seconds, much longer than usual bursts. Scientists were perplexed and excited by this unusual event, which seemed to defy the known characteristics of gamma-ray bursts. Over time, a fascinating theory emerged. This GRB could have been the result of a white hole. While we cannot definitively confirm this hypothesis, the unusual nature of the event has prompted scientists to explore new and unknown possibilities. Even after extensive study by powerful telescopes like Hubble, scientists remain uncertain about the true nature of this phenomenon. It remains a cosmic mystery, posing challenges to our current understanding of the universe. Our grasp of the universe is still incomplete, and while general relativity explains gravity, it struggles to account for the peculiarities of black holes, white holes, and their associated singularities. The intense energy and distortion of space inside these cosmic objects make it impossible for general relativity to fully explain what happens within them. As we continue to explore the cosmos, we find that many concepts once relegated to science fiction, such as wormholes, may actually have a basis in reality. These theoretical tunnels through space-time could allow for shortcuts between distant regions of the universe, or even different universes. While both white holes and wormholes are still speculative, they challenge our understanding of physics and raise the possibility of groundbreaking discoveries.